So we're going to add a new way of representing waves, but let's just go ahead and review some of the ways that we've represented waves in the past. The most common thing we've done is as sinusoidal curves in space. So in this case, along the y-axis, we're plotting out the function f of x that represents the wave, and then along the horizontal axis, we have our variable x representing the position in space. We've also talked about sinusoidal curves in time, where similarly we're plotting the wave function f of x on the y-axis, but in this case we're plotting t along the horizontal axis. Both of these are one-dimensional representations of waves. We've also talked about the phasor, where we're using a vector that is rotating in the xy plane. The length of the vector is representing the amplitude, and then the angle, theta, is the phase angle determined by kx minus omega t plus phi naught. This is also a one-dimensional representation where we can either choose the real axis or imaginary axis to represent our function f of x. What we're going to talk about is wavefronts, and this can be used as primarily a 2D or 3D representation of waves. A wavefront is simply a surface of constant phase. So basically what we're going to assume is that our wave is only varying along the x-axis in this case, which means that the wave amplitude and wave phase are independent of y and z. They only depend on x. So we're still keeping the same spatial dependence kx minus omega t plus phi naught for our waves. So just to kind of give you an example, what would wavefronts look like in 1D? Well, basically what it would do is these would be points of constant phase. All of the points that have the same phase, in this case I've just arbitrarily chosen the pi over 2 point, and so in our wavefront representation it would be a point wherever the phase is equal to pi over 2 in space. And then if this was a traveling wave, these points would move along with the wave. The distance between the wavefronts is going to be the wavelength lambda. This isn't very useful, and so it makes more sense to talk about this in 2D or 3D. So here again we have our wave, but now when I'm plotting things on the y-axis, I'm actually plotting the y dimension in space. And so what this means is that the wave is occurring all along the y-axis as well as the x-axis, but we only see variation along the x-axis. So one way to think of this is to imagine water waves that are moving in this direction where we see the wave crests along our y dimension. And so for this one, I've just arbitrarily chosen the theta equals 0 point, and then this is just repeated every integral multiple of 2 pi. And so this then down here is my graphical representation of the wave fronts. And so these will be straight lines. What this is saying is that everywhere along this line, I know that the phase of the angle is a constant. In this case, I've chosen it to be 0 plus 2 pi n. So everywhere along this particular wavefront, theta is 0. Everywhere along this wavefront, theta is equal to 2 pi. Everywhere on this wavefront, then theta is equal to 4 pi. So in 3 dimensions, what we have is the wave, again, only varies in the x direction, but we still have an amplitude in the y and z direction. So now we actually have 3-dimensional surfaces that are representing the constant phase on the wave. So I've chosen here this particular valley, which is occurring at 3 pi over 2. And so this surface right here represents a surface of constant phase. Everywhere along that surface, the phase is going to be 3 pi over 2. Everywhere along this surface, we have the same phase, and everywhere along this surface. And again, the distance between the two wavefronts is always going to be equal to the wavelength. So these are referred to as plane waves. They are essentially infinite planes. These are idealized, and so we're assuming that the electric field is extending to infinity in all directions. Now, the reason that we like to talk about plane waves is this is a simple solution to the wave equation, but it turns out that any 3D wave can be written as a sum of plane waves. So any sort of complex wave situation that we come up with, we can actually have a sum of plane waves. This means that if we know how a plane wave behaves in a particular circumstance, then we can extrapolate how the waves are going to behave for more complex waves. One other thing I should point out, these surfaces don't necessarily have constant amplitude, but they do have constant phase. And so when we get to the case of the laser, we'll see that the wavefronts actually have a varying amplitude along that wavefront, even though the phase is constant.